A single rectangular loop of wire is situated partially inside a region of uniform magnetic field of 0.45 Tesla, and part is outside of the field. The total resistance of the loop is 0.23 ohms. Calculate how much force it takes to pull the loop from the field at a constant velocity. So that means the force of you pulling on this thing is equal to the force that's pulling to the left. And that velocity needs to be 3.4 meters per second. Neglect gravity. All right, I got to warn you on this one. This is a pretty tough problem, and I'm going to go kind of fast, so fasten your seatbelt, and you might have to watch it 2 or 3 times. Magnetic flux is a tough topic, but let's jump in. All right, so a couple quick definitions for you. For this one, you need to use the idea of magnetic flux, which is how much magnetic field passes through a region. And it's just the strength of the magnetic field times the area that it's going through. So right now, the flux right here would just be the strength of this magnetic field times this region, the region that's still in the magnetic field. And anytime you have a change in flux, if the flux either is increasing or decreasing through that loop of wire, a voltage is actually created in the wire, one of the most important discoveries in physics. And the formula for that is pretty simple. The voltage that you get in the wire is just change in flux of B divided by change in T. How much your magnetic flux changes divided by how long it took to have that change. For you calculus people, if it makes you feel better, this formula will do the trick too. It's just the time derivative of magnetic flux. But you don't have to know this necessarily. But if you like calculus, this is really kind of the big boy version of it. All right, so let's actually start working this thing. So I actually made kind of a big jump here. What I did is, since flux of B is equal to B times A, the magnetic field times the area, then I just threw that definition into this formula. So instead of B equals change in flux of B, I said the voltage is, by writing the change of flux of B, it's really just the magnetic field times how much your area that's actually in the magnetic field changes. So how much this amount of area is changing throughout the problem. So I rewrote this as V equals B times delta A, the change in area, divided by the change in time. This is a really important step. So if you can see this, that'll do you well. It's how quickly the amount of area is changing in this rectangle every second. So for the next step, I got an expression for delta A, for how much the area is changing that's actually in the region of magnetic field. And what that is if you want to find out how much the area changed, how much more or less of this loop ended up in the magnetic field, then it's 0.35, which is the width of the wire, times what distance you pulled it this way. And that'll carve out a little rectangle, and that tells you how much your area changed as you moved it from here to here. It would be the area of this white rectangle. And that's 0.35 times the distance you pulled it. I'm just going to call that D for now. So we have an expression where our voltage is equal to magnetic field times 0.35 times D divided by T. Well, here's the awesome part, is we have distance and time. And they actually told us that in the problem. They said it's going at a velocity of 3.4. So we don't know distance and we don't know time, but with velocity it's sort of like we know both. We know that this chunk of stuff is equal to 3.4. So if I rewrite this whole thing, we get the voltage is equal to B times 0.35 times 3.4. And we can figure out the voltage in that wire. Alright, so just throwing it in the calculator, it looks like we have 0.54 volts created in this wire because of the changing magnetic flux when you pull it out. All right, that's a big step. We actually don't have much to go to figure out what the force is that it takes to actually pull on this wire to make that happen. So let's jump into that. So for the next step, they told us, we figured out what the voltage was, and they told us the resistance, so you know you're going to need to know that for the problem. If we have voltage and resistance, we can calculate current, and just using Ohm's law, you get 2.35, pretty easy, we've been here before. And then there's only one more step. So what I did is I used the power formula, P equals IV, and since we know V and I could throw that in, and it's also equal to force times velocity. This is a little v.